Hello, these are the solutions to recitation activity 6. First question, what is the frequency of a photon with a wavelength of 625 nanometers? Let's remember that 1 hertz is equal to 1 inverse seconds. And so it's a number of wavelength cycles. If you're thinking of light traveling, a wavelength is how long it takes in distance for a wave cycle of light to complete. So this would be the wavelength distance here. So the distance that this travels, that's our length, is equal to the wavelength. And then how many of these cycles complete, wavelength cycles complete per second, is the frequency. And their product, so lambda times nu, is equal to the speed of light. And so we should be able to solve for the frequency. This is the symbol nu. By taking the speed of light divided by the wavelength. Speed of light 2.998 times 10 to the 8 meters per second. I like to use at least 4 sig figs in the speed of light. Divide by 625 nanometers. Nanometer is very common for light. So a nanometer, 1 nanometer is a 10 to the minus 9 meter. So I can enter this 2.998 E8 and then divide by 625 e to the minus 9. If I convert to scientific notation, that's 4.80 times 10 to the 14 inverse seconds, or 4.80 times 10 to the 14 hertz. So we have a photon with a wavelength of 2575 nanometers. And what region of the electromagnetic spectrum does this radiation fall into? Well, here's what I hope we know. I hope we know that the 400 nanometer to 750 nanometer region is the visible. Then I hope that we know that the region shorter in wavelength than this is the ultraviolet, even shorter is X-ray, even shorter is gamma ray. So gamma rays, X-rays, these are our high energy side of the spectrum. And then our lower energy side is on the greater wavelength side. So the greater wavelength side would be the IR region, then the microwave, and then followed by the radio frequency, RF. And this is our lower energy side of the electromagnetic spectrum. And so I don't really expect that you know the cutoffs, other than the visible cutoffs, I think are worth knowing. And so then when we look at the choices, I think we can rule out some of them. So I think the choices are going to be kind of like, we might have a hard time deciding, is it IR or microwave, but if you notice, we don't have those choices. Ultraviolet doesn't make any sense because UV rays have to be shorter than 400 nanometer. Visible is only 400 to 750. Radio frequency is very long. These are on the units of about 1 meter, not on the nanometer side. So radio frequency, very long wavelengths. So that's not a radio frequency. So the only reasonable choice here would be infrared. Question 3, what laser emits, a laser emits radiation with an energy of 525 kJs per mole of photons. What's the wavelength of the light? Well, the way energy relates to wavelength and frequencies, the energy of a given photon is equal to h nu, equal to hc over lambda, where h is Planck's constant, where h is equal to 6.626 times 10 to the minus 34, and the units are joules times seconds. And so then what we need to do is we need to calculate the energy of just one photon. So what's the energy of one photon? Well, if it's 525 kJs per mole, 1 mole of photons is an Avogadro's number of photons. So that's the energy per photon in kilojoules. A kilojoule is 1,000 joules. And so the energy per photon is 525 divided by Avogadro's number, 6.022 E23, and then times 1,000. And so the energy per photon of this radiation is 8.718 times 10 to the minus 18 joules. And so that's the energy per photon. And so we need to put the energy of just a single photon into this equation here. So hc over lambda is equal to my photon energy of 8 excuse me 8.718 times 10 to the minus 19 joules. And so I take my wavelength is equal to hc divided by this energy. And then let me just sub in my h times c, so that should be 6.626 joules times seconds, and then times the 2.998 times 10 to the 8 meters per second. So the per second cancels into the time seconds, and then the joule cancels. My only unit here is a wavelength in unit of meters. And so let's work this out. So I'm going to take 6.626 e minus 34 times 2.998 e to the 8 and divide by 8.718 times 10 to the minus 19, and I get 2.27, call it 2.29. Oh, I'm sorry, 2.28 times 10 to the minus 1, 2, 3, 4, 5, 6, 7, and that's units of meters. Let's convert that to nanometers, because it wants the answer in nanometers. So 1 meter contains a lot of nanometers, 10 to the plus 9 nanometers. So multiplying by 1e9, or 10 to the 9, is 228 nanometers. So 228 nanometer light is well into the ultraviolet region. So a really high energy per photon, 525 kilojoules per mole. Now, in UV rays of the sunlight, we would be worried about wavelengths in this region here because that energy is so high that it's capable of being absorbed into our skin, breaking bonds in the DNA, causing radicals to form that can then cause disruptions in our skin, leading to potential skin cancer. So this is one of the reasons why you want to be worried about UV rays, is because they have enough energy to start breaking bonds in your body and causing harm as a result. So moving on to question 4. So copper metal must absorb radiation with a minimum frequency of 1.15 times 10 to the 5 hertz. For an electron to be ejected, what wavelengths of light can cause this electron to be ejected? Now, first, let's talk about the photoelectric effect. The idea here is that if you have a metal surface, imagine you have a piece of metal, we're going to shine light onto the metal, and then the question is, do electrons become ejected off the surface of the metal? The answer is light has to have some minimum frequency. If we use light of too low frequency, then we don't have enough energy to break the attractive force for the electron to the nucleus of the metal that holds on to the electron. And so we have to use light of minimum frequency. And then if we use light greater than this frequency, then we can cause the electrons to be ejected. And then the excess energy that the molecule has would be energy that the electron has to fly away with. It would be the kinetic energy that that electron has to move away from that metal surface. And so you can sort of see that the ionization energy of the metal would be calculated from this energy here. The energy of our photon is equal to h nu, where h is Planck's constant, joules times seconds, times the unit in hertz of inverse seconds. Let's actually work this out real quick, because we can actually see that the energy that this photon has that minimally causes an electron to be ejected from this metal, we take 6.626 times 10 to the minus 34 joules times seconds times 1.15 times 10 to the 15 inverse seconds. Inverse seconds cancels into seconds. And so this tells us that the metal surface has an ionization energy per atom, 6.626 times 10 to the minus 34 times 1.15 e to the 15. And so that's 7.62 times 10 to the minus 19 joules. And so if we use a photon lower in energy, lower in frequency than 1.15 times 10 to the 15 hertz, and we don't have enough energy to break that electron free from the metal. And so then if we use a frequency greater than 1.15 times 10 to the 15 hertz, then we do have excess energy. Imagine we use 7.63 times 10 to the minus 19 joules. Then that photon, that electron that we break free from the metal has 0.01 times 10 to the minus 19 joules of excess energy that it uses to fly away with. And that then goes into that energy being kinetic energy, 1/2 mv squared. The electron has a mass. You could calculate, or you can consider or understand that the more excess energy that we give the electron, then the higher the velocity it flies away with. But anyways, that's really not part of this question here. Part of this question here is just saying, well, what wavelengths cause this event to take place? We know that we want the energy of our photon equal to h nu, that we want the energy of that photon to be greater than or equal to 7.62 times 10 to the minus 19 joules. We want the frequency to be greater than or equal to this minimum value, 1.15 hertz. Well, what about the wavelength? Well, c is equal to lambda times nu. And so when we calculate our wavelength associated with this transition, let's do that. So the wavelength associated with this transition, c over nu. So I'm just going to do the math without showing it, but 2.998 e to the 8 for the speed of light, divide by 1.15 e to the 15 for the frequency. That's 2.61 times 10 to the minus 7, converted over nanometers times 1e9 to convert to nanometers is 261 nanometers. But now, do we want this wavelength to be this value or greater, or this value or lower? And the key is we want the value to be this wavelength or lower, because that's what goes to a greater energy. Energy of our photon is equal to hc over lambda. If we go to a lower wavelength, we go to a greater energy. And so we need a greater energy photon, which is achieved with a higher frequency or with a lower wavelength. So we want to go to wavelengths less than 261 nanometers. And so 380 just doesn't make sense. That's not the right number. And then the right number is 261 nanometers. We want to be that wavelength or greater to cause an electron to be ejected. And then I suppose we did have to calculate the ionization energy, because it says, well, what's the ionization energy of copper, but in kJs per mole? Well, the ionization energy of copper in joules per atom is 7.62 times 10 to the minus 19 joules, as we calculated earlier. So the minimum frequency that's needed to cause an electron to be ejected is telling us the ionization energy. It's directly related to that ionization energy of the atom. So the ionization energy of one copper atom we saw was equal to 7.62 times 10 to the minus 19 joules. And so the ionization energy in kJs per mole would be found just by taking this number of joules here. That's the joules per copper atom. There's an Avogadro's number of copper atoms and a mole of copper. And then there's 1,000 joules in a kilojoule. So if we take that energy 7.62 times 10 to the minus 19 times Avogadro's number, so 7.62 E19 negative times 6.022 e to the 23 divided by 1,000 is 459 kJs per mole. So that would be the energy it takes to ionize a mole of copper, 459 kJs per mole. So what we have to do is realize the photoelectric effect is relating one photon interacts with one atom. We can calculate the photon energy. That tells us something about the one atom's ionization energy. Then we just convert over to kJs per mole for the ionization energy in that unit. So moving on, question 5. Actually, there's 2 questions here, but what transition leads to the 411 line in the H atom emission spectrum? So hydrogen atom, when we take a sample of hydrogen, like an H2 gas sample, we convert it with high voltage of energy. That's high voltage HV is what that's meaning there. We break this into 2 H atoms. These are generally going to be what we call like hot atoms that then can coalesce back down towards their ground state. And so then we see things that kind of look like this, where we have these different energy levels, 1, 2, 3, 4, etc. We can have like the 4 to 2, the 3 to 2. We can have 4 to 1 transitions, 3 to 1, 2 to 1 transitions. We have all these different transitions that are possible. The transitions all the way back to n equals 1 are the greatest energy transitions. The ones that stop at 2 are a lower energy set of transitions, but these are the ones, the 4 to 2, the 3 to 2, transitions that occur in the visible region. The 4 to 1, 3 to 1, 2 to 1, these 3 transitions here are in the UV region. And so we could see those if we looked in like an ultraviolet region, but the H atom has 4 lines that are in the visible region, the 6 to 2, 5 to 2, 4 to 2, and 3 to 2 transitions. And so the 411 line of the H atom emission spectrum, if we're thinking in terms of the if we're thinking just in terms of the visible region, 400 to 750 nanometers, this is the higher energy side of that spectrum. And H atom has 3 other transitions that are on the lower energy, higher wavelength side. There's really nowhere else for them to be. If you think, if I'm going to have 3 other transitions for H atom, are they likely to be between 400 and 410 nanometers, or between 412 and 750 nanometers? And the answer is the other 4 transitions are going to be at greater wavelengths, which are lower energy transitions. And so if we think of these transitions here for 5 to 2 and 6 to 2, that 6 to 2 transition of those ones that go to the 2 value, so the 6 to 2, 5 to 2, 4 to 2, 3 to 2, has the greatest difference of energy. And so without even plugging in any numbers here, I should be able to see that the 6 to 2 transition of the atom is the one that leads to that emission. Light's emitted by an atom when it's in the high energy state. And so these states here, the hidden axis going up here is energy. So when the atoms are up here in high energy, they're trying to fall back or reduce energy down to a lower energy state. And when they do so, they're getting closer to being back toward a low energy H atom, which can then collide back with another H atom to remake H2, because we simply have a light source that's breaking H2, allowing H atoms to form. They eventually reform H2, so we continue to have a functioning light source, which is just absorbing high voltage energy to keep breaking those bonds. So what goes on in a light source here is H2 is just continually breaking its bond. Some of the atoms are hot. We see the emission given off. Some of the atoms recombine, we make H2, and this cycle repeats itself. And so now if we want to show this, we could show this using math and the Bohr model equations. The energy as a function of N for hydrogen is equal to negative 2.179 times 10 to the minus 18 joules times the 1 over the N value squared for the H atom. So we could go ahead and plug in our final state of 2 minus our final state of 6 and plug into this equation here and get the change of energy for the H atom. The hydrogen atom's losing energy when it goes from 6 to 2. It's high energy in 6, lower energy in 2. So the H atom, the energy it loses, where does it go? It goes into the creation of the photon. So the energy lost by the H atom is gained by the photon. Now we could do the opposite. You could take H atom from n equals 2 to n equals 6. You just have to have the absorption of the radiation to take you from n equals 2 to 6. So absorption goes from low to high N, and emission goes from high to low N. And so by emission, we mean light given off, like permeating away from the tube of gas. And then absorption would be, if we're like shining light inward on the reaction, it would be absorbing those photons. And so absorption to go up, let me change color of my pen here. So if we want to have an absorption event to go upward, that's absorption. and then emission is where we fall back downward. Okay, so the emission here has to be the greater energy, n equals 6 to the n equals 2 transition. And so this is our final state, and then the 6 is our initial state. And you can plug into the equation, get your delta E, and convert that delta E over to joules, and then set that equal to hc over lambda, calculate a wavelength. I'm not going to show that here, but you can do that if you wish. And so then for the next question here, which transition below for an electron in an H atom leads to an emission of a photon with the greatest wavelength? So the greatest wavelength, to have a greater wavelength, means it's a lower energy transition. And so then emission, again, is from high N to low N. That's emission, means light's emitted, and then light would be absorbed by the opposite. If we go from low to high N, then that could be accomplished by the absorption of light. And so to have emission, we have to go from high to low, and then this is going to be the lower energy, 3 to 2. So N equals 3 to 2. That's the greater wavelength, lower energy transition of these four that are shown here. And then the 6 to 2 would be the lower wavelength, basically a paired question, very similar to the question above. I think the second question is more direct, that you should be able to answer it without doing any math, just by understanding the relationship of wavelength to energy, that it's longer wavelengths corresponding to lower energies, and we're looking for the lower energy high end to low end transition. And then the first example is maybe a little confusing on whether or not you actually need to do a calculation or not, but I think we can avoid that just by thinking of this transition being so close to the edge of the high energy side of the UV region that this has to be the higher energy of those four visible peaks for the H atom. And I think we should kind of generally know the idea that the transitions ending in 2 happen to be the ones that fall in the UV region. If you look at the 4 to 3 transitions, the 5 to 4 transition, the 6 to 5, or the 6 all the way down to 3, if you look at those transitions, these are in the IR region, lower energy region of the electromagnetic spectrum. And then, as we mentioned, the ones that fall all the way to 1 are in the ultraviolet region. Moving on to question 6. Which of the following sets of quantum numbers are allowed by an electron in an atom? And so let's talk about our quantum numbers real quick. So we have 4 quantum numbers that are relating to the location of electrons, or how we can describe electrons in multi-electron atoms. N is the quantum number relating to the size of the orbital containing the electron. L relates to the shape of the orbital. M sub L relates to the direction or the orientation of the orbital. And then the M sub S is about the spin. Let's start with M sub S. M sub S is either plus 1/2 or minus 1/2. And if we're thinking of an electron in an orbital, let's say like a spherical s orbital, it just means the electron can spin one direction or it can spin the opposite direction. So it can spin kind of one way around the circle, or it can spin the other way around the circle. So you can have kind of clockwise or counterclockwise spin is sort of the idea here. So imagine you have clockwise spin or counterclockwise spin. Now, we don't define the plus or the minus to be either one of those spins. Technically, it's with the field as plus 1/2 against the applied field as minus 1/2. But the whole idea is you can have 2 electrons in every orbital, and they can either be up or down in terms of their relative spin. Now, size of the orbital is relating to n. The smallest n can be as 1, 2, 3 on upward. So the n value can take integral values, but starting at 1. L takes on values starting at 0 upward, but it only goes up to the n minus 1 value. And so it gets a little bit confusing, but when you start thinking of possible n values, if you have an n of 1, then L can only be 0, because the next L value possible of 1 is not achievable, because the highest L can be is n minus 1. This then starts to get into the shape, that an L shape is an s orbital for 0, p for 1. If you go to 2, that's a d shape. 3 is F-shaped orbitals, and the L is really relating to like the angular or sort of the sort of planes of no probability of finding electron through the nucleus of the atom. And so if you look at an S, it has none of those. If you look at a p orbital, it has one of those planes right through the center of the atom. So that's our p-shaped orbital. If you look at the D-shaped orbital, they mostly look like clover leaves, so you have two planes. And then if you look at the F-shaped orbitals, and oddly the book doesn't actually even show any of the F orbitals, but if you look at the F orbitals, they kind of have three sets of lobes, so that you have 1, 2, 3 planes. So you have 0 for S, 1 for P, 2 for D, and then 3 for F. And there's some, peculiar looking orbitals. There's one of these D orbitals that has like a donut ring. If you look at some of the F, I'll show you these in class. There's some that have like multiple donut rings. So it's maybe not easy to always tell with every orbital, but the idea is that you have, 0 versus 1 versus 2 versus 3 angular nodes through the atom. That's what the L value is relating to. The M sub L is telling you how many different orbitals are possible through the directions that those orbitals can point. The range of values for M sub L is from minus L through 0 to plus L, all the integers in between. And then lastly, we already mentioned the spin up or down. So the idea here, just to go through a couple combinations, would be like if n is equal to 1, the only L value is 0, and then the only M sub L is 0, and then the M sub S could be plus or minus a half. And so this is kind of telling you that the n equals 1 shell is just one orbital that can have either one electron or two electrons, and that's helping you understand hydrogen versus helium, hydrogen being a 1s1, helium being a 1s2. Then if you move to the next row of the periodic table, if you move to like lithium, beryllium, onto boron, etc., these are using the n equals 2 shell. L equals 0, L equals 1 are possible. When L equals 0, the only M sub L possible is 0, because that's the 2s orbital. So we have the 2s that can take on 2 electrons, or up to 2 electrons, for describing lithium and beryllium. And then if you move on to L equals 1, the possible range of M sub L's is minus 1, 0, plus 1. And so that's 1, 2, 3. That's our 3 sets of 2p orbitals. So we have the 2p orbitals. There's 3 of them. We can put 3 electrons in, 3 more electrons in. This is describing boron through neon. So those 6 elements falling into those configurations of 1s2, 2s2, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6, all the way across that second row of the periodic table. And so coming back to question 6 now, taking a look at it, which range of values is not possible? N3, L1, M sub L minus 2, that M sub L is not possible because it can only go from minus L to plus L. Now, there's a lot of confusing parts here where you might say, well, if n is 3, can't L be 2? But what you have to realize is that the n and L values, they're telling you for that particular n and L combination, which the n equals 3, L equals 1, that's the combination that's talking about a 3p subshell, of which there are 3 possible orbitals, the minus 1, 0, 1 M sub L combinations. And so this M sub L, let me erase it here, the M sub L combination minus 2 is just not possible for that L value. And so you could have an n equals 3, L equals 2 orbital for which that would be a possible M sub L value, but it would have to have an L of 2, not an L of 1. Okay, and so likewise for 2, the L value is not possible because L has the max value of n minus 1. And so N2 can only go up to L0 or L1, not to L2. So that's an impossible L value. So both of those sets are not possible. So which of the following sets of quantum numbers are allowed? It would be neither one of those two. And then what is the designation for the n equals 4, L equals 2? So that would be a 4D. So 4D because the L equals 2 is defining the D shape. And then this is our size, so that's the 4th shell d orbital, so the 4d. Question 7, what's the max number of electrons that can occupy a 5f subshell? So a 5f subshell, let's think here, that would be n equals 5. The L shape of f excuse me, the shape of an F orbital is L equals 3. And so then think of the m sub l's that are possible for L3, be minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. So that's 1, 2, 3, 4, 5, 6, 7. And so that's 7 orbitals that are possible. 1, 2, 3, 4, 5, 6. So I need one more. And so these could be the description of our 5F subshell. 5F is actually the second of the possible F subshells for our ground state atoms. 4F would be the first for n equals 4, L equals 3. It's the first because that's the first time L is allowed to be 3. If you go to n equals 3, the highest L can be is 2. So the first time we have an F block is when we have the 4F subshell. It also would have 7 different orbitals that are possible, and each one of those orbitals, because they each can have the m sub s of plus and minus a half, so the maximum number of electrons here that can occupy that subshell would be 14. And so this is kind of why our periodic table has an S block that's 2 elements across, because S blocks can fill 2 electrons can fill into that block. We have a P block that has 6 elements across. That's like our boron across the neon group of elements. Those go 6 across. Our transition metals are 10 across because those are filling into D subshells, or last placing electrons into D subshells. And so D subshells can take on 10 electrons total. And then our lanthanide and actinide series go up to 14 electrons because 7 times 2, we have 7 different orbitals that are possible that we can fill 2 electrons into each. And then, sort of sadly, we can't keep packing electrons around atoms, at least for in a stable way. So we have not yet, as scientists, been able to generate any atoms that in their ground state use atoms past F. The next set of orbitals would be G. That would be the n equals at least 5, L equals 4 combination. So elements that big just have not yet been able to be created. And if they were, I doubt they'd have any reasonable lifetime or practical utility. Okay, so 14 is the number of electrons that can occupy the 5F subshell. What's the range of possible magnetic quantum numbers, the m sub l values for this orbital below? So this orbital below, the key is for me is that this is one orbital. It's like this is a orbital. This isn't like 2 orbitals. This is one of the d orbitals. And so the key that I see here is 1, 2 planes of symmetry through those sets of lobes. And so this is a d orbital. And so then a d orbital has an L of 2. So the m sub l range is equal to minus 2, minus 1, 0, plus 1, plus 2. And so that would be 5 different possible combinations. Looks like I just covered up the figure. I'll try to fix this. Looks like I'm covering up the or 2 from the answer for C. So the range of m sub l's goes from minus 2, minus 1, 0, 1, or 2. How many unpaired electrons does a ground state sulfur atom contain? So let's look at the ground state configuration for sulfur. Sulfur's in the 3rd row of the periodic table. If we're doing the complete configuration, I just look at a periodic table and kind of start looking at, I need through the 1s2 to get through hydrogen and helium. I got to go through the next 2 elements across. That's the 2s2 into the s block, so 2s2. I got to get across a p block, so that's 6 across. That's a 2p6. And then I come to the 3s2 for sodium and magnesium. And then finally, I'm in the 3p and sulfur's 4 across. And so I can also double check here. Sulfur is the 16th element. And so I should have 16 electrons being distributed. So that's 10, 12, 4 for 16 total electrons. So that's good. So a little double check there. And so then if I'm picturing a diagram, I could picture it like this. This might not be the most intuitive thing in the world. And I could be placing my electrons in for the 1s2, 2s2, 2p6. I try to maximize the spin of the electrons, but then I have to pair 3s2, and then maximizing the spin. This is the use of what we call Hund's rule. And so Hund's rule says that you have to maximize the spin of the electrons, spread them out into the different orbitals. That would be, as opposed to doing this process here, this would be the wrong configuration. This would be a Hund's rule violation. So that would be the wrong configuration for sulfur. So we should have maximizing the spin, and then I can't maximize the spin this way because now that violates the Pauli exclusion principle because both those electrons would have the same set of 4 quantum numbers. So I have to pair their spins together, one up, one down, like so. And so this would be our configuration here. Now, perhaps what's confusing with the electron configurations is that if we had sketched the configuration this way, maybe it would make more sense that the 1s is the lowest energy orbital, then the 2s orbital higher in energy, then our 2p set of orbitals the next highest, then we would have our 3s, and then our 3p. And you can think of how presumably the energies of our orbitals, if we were to keep going up in energy, are going to start getting closer together, kind of like how the Bohr model did. So our n equals 4 orbital coming next for the 4s would be around here. And then we'd have our 3D set of orbitals coming next. How to know the 3D come next? Well, they're the next set of elements that fill their electrons into the D shell next, and we have our 4p. And then these energies start to get a lot closer together as we go higher in energy, just kind of like how when we looked at the Bohr model, we went n equals 1 to 2 to 3 to 4 to 5, how those energy levels started getting closer together. The same thing happens for our elements. We're just putting 2, 4, 6 more, 2 more, and then our last 4 electrons in. And so then if we continue putting electrons in, if you imagine we're trying to get to something, say, like titanium, which has the 4s2 configuration, so we cap off our 3p, then our 4s2, then the 2 electrons into the 3d. So it would be a 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. Then, of course, you can say, well, all of this is just equal to argon. So you could say that titanium, for example, would be an argon 4s2, 3d2. Now the last question here gets at anomalies. Sometimes the configuration is not the one we expect. We would expect a configuration might look like something like a krypton 5s2, 4d4, and so this 5s2 configuration, just making sure I show that more clearly, the 5s2, we'd expect this configuration, then we'd expect the 4d4 for this element here. The element that's consistent with krypton having 36 electrons, plus 2 plus 4, or plus 1 plus 5, this is a 5 here, that this would be the element that has 42 electrons. So you're just looking for an element with 42 protons, or an element with the 42nd atomic number. And so that would be molybdenum. And so then not for 4, though, it'd be molybdenum for 6, for having 6 unpaired electrons. This is what we expect. That's our expected configuration. Now the anomaly, the unexpected configuration, is the 4s1, excuse me, the 5s1, 4d5. And so we have all 6 of those electrons spin unpaired. So it'd be molybdenum for 6 unpaired electrons. All right, that completes this video. Have a great week.